So in the next bit, we have to consider a triangle P in the Z plane with vertices I, 1 minus I, and 1 plus I. They are placed at those points. So we have to determine the triangle P naught or P0, which mapped P under the transformation. So this is about conformal transformation, conformal mapping. So transformation is given by the equation W is equal to 3z plus 4 minus 2i. So also we have to find the relation between P and P naught and calculate the area magnification. So this is about conformal mapping. If you would see the vertices that have been provided to us, we'll have the solution to the given question like this. So if we are to look at the triangle P over here, we map it in the, well, we just draw it in the xy or the z plane consisting of the x-axis and the y-axis, the x-axis being the real one and the y-axis being the imaginary. So this is x, that's y over there. So the imaginary axis is having the I coordinates and the real number coordinates, that is 1, 2 and 3, they continue in the x-axis. Now if we are to determine those vertices over there, so one of the vertices is I, which is right there at the top along the y-axis, the positive y-axis, and the next one is 1 minus I. So 1 is the real number, so it's along the real axis, that is the x-axis over there, and 1 minus I corresponds to the point which is there in the imaginary and real plane uh, there at the down. So this is 1 minus I and this is 1 plus I. So these are the values and this is I as I just mentioned. So now let's look at the P naught. Well, for obtaining the triangle P naught, the transformation that we have to consider is W is equal to 3 times of Z. Now Z is simply x plus IY. So 3 times of x plus IY plus 4 minus 2I. Now this can be rewritten with the real and the imaginary terms separated. So this is 3x plus 4 and this is I in common to y minus 2. So this is what we have as the value of W, the transformation equation. We'll see whether the transformation equation is a linear one or probably something else. Now, in order to map the P naught triangle, first of all, we have to consider this will be in the W plane. Now, first of all, we have to consider the values over there. So we'll be putting the values of x and y, the separate values of x and y. Now, the first value that we had over here is I. Now, for that value, we have the value of x to be equal to 0 and we have the value of y to be simply equal to 1 because that's I times of 1 and the value of x, the real part, doesn't exist in that point at that point. So x is equal to 0, we put x is equal to 0. Now this equation here is the form of u plus iv. So we have a value of u and we have a value of v. Now here x is equal to 0 gives me u to be equal to only 4, and for y is equal to I have the value of v to be equal to well, if I put that value as 1, so y minus 2 is 1, and because I goes common in that, so y minus 2 is 1, so y is going to be equal to, well, actually it's not y minus 2 is equal to 1, in fact it's the value of y is in fact I or 1 simply. So I put the value of y as 1 and 1 minus 2 gives me -1. So the value of v is -1 multiplied to I, that gives me IV. So this is the first case, the first coordinates that we are going to get in the W plane, having the value of u and v. So the first set of values have been obtained over here. Now the second set has the coordinates, that is, for x we are getting the value to be equal to 1, and for y we have the value as -I. And if we substitute those values, -I means actually here also y is equal to 1, and here y will be equal to -1, because I is simply in the imaginary coordinate or the imaginary axis. So we'll be just considering the value over there instead of taking the imaginary term. So as a result of that, we'll be getting the value of u over here, which is in reference to this equation that we have at hand. So with x being equal to 1, we have the value of u to be 7, and with y to be equal to -1, we have the value of v to be equal to -1 as well. I mean -3, not -1, because -1 -2 is -3. So this is the second set of values for the coordinates in the W plane that we have obtained by using these values from the first set, that is for the first set of coordinates that we have for P. And as for the third set, we have x to be equal to 1, y to be equal to 1, because it is plus I over there. So we have the value of u again goes to 7, while the value of v over here is 1 minus of 2, which is -1. So this is 7 and -1 in the W plane. We'll construct the map for that and see what happens and how they are related, because we have to obtain the relation. So here we have the points where we have the W plane over here. This is the Z plane and this is the W plane, and in the W plane we have mapped the coordinates accordingly, because we have just made the transformations and mapped them. Now going back to the equation that we have at hand for the transformation, we have it as W is equal to 3Z times of 4 plus 4 minus 2I. Now this is of the form, this has both the forms where first of all we have a constant multiplied to Z, so that makes it rotational, and then we have the second bit as the beta term, which is the translational part or the linear case. So this is the mapping here is both rotational and translational because of the equation that we see, and even the mapping that we have seen and observed at hand. It is showing rotational and a bit of magnification involved, and then also translational. Now had that been only Z plus beta, that would have been completely translational, and had that been only alpha times of Z, then we would have had the rotational, but it's a combination of both, as we can see. Now as far as the magnification is concerned, we just have to obtain fz, z naught in this case, and the square of it. The area magnification is always the square term, which involves the partial derivative of the uv function over the xy function, and then that leads to del u over del x squared plus del u over del y squared, which is in this case going to give me, now del u over del x is going to give me, we can look at this equation over there because it's w, so del u over del x squared is going to give me 9, and the second term, well, it's not going to give anything at all, because there we do not have any y term in the u case over here, so there's no y term over there, so this is going to be 0, the second term. So all we have left is the magnification. The area magnification in this case is yielding the value 9, Had this been a linear magnification that we were supposed to obtain, then it would have been 3, but the question asks about area magnification, so that's the value. Up next, we will be obtaining the Taylor series expansion of cosine squared z. Now, to simplify this, we can consider the solution by this simplification, which I think will be useful. So cosine squared z is nothing but 1 plus cosine of 2z over 2. So this is going to be an expansion of well, the half term can be taken as common, so 1 stays as such. We are only to consider the cosine 2z expansion, Taylor series expansion. Now generally the Taylor series expansion involves the uh, the form that I'm going to write down over here. That is, the first term remains as such, that is 1 added to the next case. Now the next case has the Taylor series expansion, which has to extend from n is equal to 0 to right up to infinity, and this has the value over there as 2z, that is the cosine of 2z. So that to the power n divided by n factorial dn over dzn. Now it would have been the cosine 2z function, but now having the value about a that has been asked, we will be putting the function which is z. Instead of that, we are going to put a z0. Z0 here is nothing but equal to a. So we'll be doing the derivative for sure, but we'll also be considering the value over there. Instead of z, we'll be obtaining or getting a. So in order to expand the series, we proceed as follows. Now the first term, you can spare me for the equation being it's shifted towards the left, that is to create space. But the first term that has 1, that's okay, but going to the summation over there, we have n is equal to 0, and so the bracketed term 2z to the power 0 is 1, divided by 0 factorial is 1 as well. And the derivative is obviously the term itself, because d0 divided by dz to the power 0, so that's not a derivative. So we are just having f z0 or f of a. Now f of a is going to give me cosine of 2z. Instead of 2z, it will be 2a. So that's the first term. As for the second term, we have 2z, that's all right, to the power 1, so that stays as such, and divided by 1 factorial is again 1. We'll be doing the derivative. Now the derivative of cosine is minus sine, so minus sine, and the 2 over there gets multiplied. We'll be just multiplying the 2 over here, and cosine will lead to sine, so minus sine 2a. Instead of 2z, it will be 2a. So that's the second term that we are getting. As for the third term, we'll be continuing like that. So this is 2z to the power 2 now, divided by 2 factorial, which is again 2. So this is 2z squared divided by 2 factorial, which is 2. I keep it like that. And for the derivative of the previous term, we can take the double derivative, means the derivative of the single derivative. So single derivative had yielded 2 times of minus sine 2a. So now this will be 4 times, because 2 multiplied to 2, 4 times. The sine is going to give me cosine, but the negative sign stays as such. So cosine of 2a now, and it continues like that till infinity, and we will have the value accordingly. You can put those values, you can calculate them, these 2's and the sines and the cosines that we have over here, and you can put those values and you will get the result accordingly. So that's the expansion, the Taylor series expansion of the cosine square as z about z is equal to a. In the next bit, we have to obtain the Fourier sine transform of the function f(x), which is e to the power minus ax. Pretty straightforward. How we proceed, we'll see that. So as far as the sine transform is concerned, we have the formula that is at hand is fs is equal to root over of 2 over pi integrated from 0 to infinity, because that has been provided to us. A is greater than 0, and we have the function fx over here within the integral, and sine sx, because f of s, it's that s times of dx. Now if we put the value over there, then what we get is simply e to the power minus ax sine sx dx. So we can expand that sine function over there, that is sine sx, as the exponential term e raised to the power isx minus e to the power minus isx divided by 2i. Multiplying all of that, we then follow it up with the integration. Now the integration has the exponential term multiplied to x, and that factor that is multiplied to x goes down, a minus is in the first term, a plus is in the second term. So taking the LCM, we have a squared plus s squared. Now a squared plus x squared in the denominator, the cross multiplications, we have a plus is and a minus is multiplied to both the terms in the numerator, and from that, well, we can take the a minus ix out of the equation for that for the limit part, because had we taken the by parts, the e to the power minus ax would have been excluded, and so as a result of that, we simply have the sine and the cosine term. So the 2i that was taken outside, that can now be taken in. So we have e to the power minus isx minus e to the power minus isx over 2i. That gives me the sine term, and the I cancels out with the s term, which was the with the s that was multiplied over there, the is that was there. The I cancels out with that, and we have the cosine term in the second part. Now integrating within that given limit is going to give the sine function, or the sine function is going to disappear, and the cosine function is just going to stay, because cosine of 0 is 1. So what we are left with is we can take the minus sign inside, and we have 2 root 2 over root pi, and in that second case, if we are to take the exponential term inside and all of that, we'll be getting the first term to be 0, and the second term is what is going to yield us s only, because the cosine term is going to be equal to 1, and we have a square plus x plus s square in the denominator, which I have forgotten over here. I'll probably be writing down 1 over a square plus x s square, 1 over a square plus s square, and finally over here that I've brought it back once again. So this is the result of the Fourier sine transform of the function, which is f of x is equal to e raised to the power minus ax within the given limits, for a being a positive number. In the next bit, we have to obtain the Fourier transform of the normalized Gaussian distribution. Now this is a Gaussian distribution of the having the exponential in the squared term, negative squared term, that is. and it's within that limit of minus infinity to plus infinity. So let's get started with the result. Now the Gaussian distribution, as I said, uh, first of all we'll be writing the Fourier transform equation, which is Fs is equal to 1 over of root over of 2 pi times of the integration value, which is from extending from minus infinity to plus infinity, f of t, which has been provided to us, e to the power ist. Now had there been a sine transformation, we would have had the sine function there. For a cosine transformation, we would have had the cosine transformation or cosine function there. And here it is the normal Fourier transform, which is having e to the power ist. So now we just put the value of ft over there and we proceed. Now putting the value over there, we get the equation as follows, and with that, this line that I have written over there, this is just to make things easier for us. What I've done is I have added a few things and subtracted that thing again. That is the factor that you can see, is over is over 2 root alpha squared, and even the second term in the power, I have made a small change where I have multiplied 2 root alpha and I have divided the same. Again, all of that to make things easier for calculation purpose. As you can see in the very next line, we have this whole square term. The first term and the second term remains as such, and that does not contain the t term. Now that t term containing whole square term, I have taken that to be x, and I have made the changes accordingly for the limits that were provided. And obviously x remains to be infinity, minus infinity to plus infinity for t, so the limits do not change, but the dx value that I have put over there, so dt is equal to dx over root alpha. Alpha again is a substitution for 1 over 2 tau squared, that is provided over here, and then the integration gives me the following result. I put in the value of alpha from here over to here. In this line I have put the value of alpha accordingly, and the result thus obtained is this. You can use the pen and paper and try work it out, referring to this structure that I have provided to you. And this is the entire structure that I have provided, and I have made my calculations. You can check for yourself whether they are correct or not, and then you'll see. I think it is correct. So moving over to the next question. Here we have to obtain the inverse Laplace transform of the given function, that is fs is equal to 2s minus 3 over s squared plus 2s plus 2. Now we'll have to modify this in order to obtain the solution. This is pretty straightforward with the formulas that are available to us. Even I'll be providing you with the entire section or the entire list of the formulas later in a separate video on Laplace transform. We'll be doing the Fourier transform as well, but here I'll be providing the formulas that are required over here. Now for that function that has been provided, that can be simply written as we'll look at the denominator term first. In the denominator we have s squared plus 2s plus 2. Well, that's not a whole squared term, so we'll put a whole squared term there, and we have s plus 1 whole squared plus 1 squared in the denominator, and in the numerator we have 2s minus 3. Well, to get that s plus 1, that will be necessary from the formula point of view, so we'll have 2s, and what should we add? We may add a 2 over here, so that we can take the 2 common and we have s plus 1 left, and if we are putting a 2 over there, we'll be putting a minus 2 with that minus 3, so that becomes minus 5. And so this equation now will take the form 2 times of s plus 1 over that entire term in the denominator, which is s plus 1 squared plus 1 squared, and the second term has minus 5 times of 1 over s plus 1 whole squared plus 1 squared. Well, if we are to take the Laplacian inverse of this, so the Laplace inverse of fs is going to give us the Laplace inverse of, we can take the 2 outside, the s plus 1 over s plus 1 squared plus 1 squared minus 5 times of the Laplacian inverse of 1 over s plus 1 whole squared plus 1 squared. Now this is of the form where I'm providing you with the form over here. So the Laplacian inverse of 1 over s minus a whole squared plus b squared is going to be equal to 1 over b times of e to the power at sine of bt. So that's one bit. And the Laplacian inverse of s minus a over s minus a whole squared plus b squared is going to give us e to the power at cosine of bt. So that's pretty simple. Instead of the minus a, we have the plus 1 over here. So if we were to get minus a, so a here is actually minus 1. So minus of minus 1 is plus 1 over there. So this term is going to be 2 multiplied to e to the power at, where for a we have minus 1. So this is e to the power minus t cosine of bt. B, instead of b we have 1 again, so cosine of b, which is 1 times of t. And as for the second term, we have minus 5 multiplied to e to the power, well, 1 over b is 1 over 1, so that goes to 1 only, and e to the power a is minus 1, so minus t over here, sine b again is 1, so sine t. So this is the value of the Laplacian inverse Laplace transform of the given function fs. And finally we have to obtain we have to solve this initial value problem using a Laplace transform. The equation is quite familiar, and we have the condition, the initial value conditions, that is y is equal to y naught and y prime, that is dy over dt, as v naught at the starting time, that is t is equal to 0. Now in order to solve this, we just have to take the derivative, the Laplacian of the derivative terms, and then we can obtain the value. The inverse Laplacian of the derivative terms are as follows. But before that, what I would like to suggest is that for convenience, I would like to take this as f of 0, which is the initial part of the function, if I take that above term as the function, and this one as f primed of 0, which is equal to v0 or v naught that has been provided. To begin with, I'm just providing you with the Laplacian of the derivatives. So the Laplacian of the first order derivative, that is f primed, that is df over dt, in this case dy over dt, is going to be s times of the Laplacian of f of t, as I've shown you over there. Laplacian of the f of t is going to be f of s, which I have provided over here. So, and that minus f of 0. Again, if I take the double derivative, that is f double primed, this is double primed, so f double primed of t, then we have s squared f of s minus s times of f of 0 minus f primed, that is the first order derivative, and the value being 0 over there. So we are going to put all of this in the above equation, and we take the Laplacian of it, and the Laplacian of the right hand side, obviously cosine omega t, is as we know, is going to be as follows, that I'm going to write over here. Now we take the Laplacian and we put those values over there, and putting those values on the right hand side, we have the Laplacian of the cosine omega t term, which is s over s squared plus omega squared, and the left hand side the double derivative term, and the Laplacian of y is fs in this case. Now we proceed till the end, and we take everything to the right hand side and we just keep fs, so that the inverse Laplacian is going to give me the value of y, and that is exactly what I have done. Taken the values onto the right hand side and divided the multiplied terms. The multiplied term on the left hand side was s squared plus omega squared, which was divided to the right hand side, and we obtained then we took the inverse Laplacian of it, and the inverse Laplacian not the Laplacian, the inverse Laplace transform gave us the corresponding results, which is as shown. So this is the value that was to be, this was the solution of the given, of the provided equation. Now because the values were y naught and v naught for the initial values, had they been 0 it would have been much simpler, but nevertheless it's the solution that was asked for. So that's all from the second part of the assignment. We'll be doing a few more topics in the later upcoming videos. Till then, thank you for watching.